Hi, Benjamin.
Hello? You guys hear me? Okay. My mic wasn't working earlier, so I just had to test it again.
No, he shaved.
And my fiance was complaining too much, so I shaved.
For a second, I thought the meme got to you.
Memes don't get to me, but my fiance does.
Smart man. Oh, Professor, for the ANSYS download, it's Discovery Student or just Student or
Just the
SC.
student version. So the student version, that's closest to what you would see in kind of the professional ANSYS interface. So we're going to use that one.
Gotcha. Okay. Is it R1 or R2? This is kind of confusing. How many different?
Yeah, so those are because so they update the software every year. For the things that we're going to be doing in this class, it shouldn't matter because we're doing pretty much the basics of ANSYS, and so their updates are more for like the professional users. So for us, it doesn't matter too much.
Gotcha.
Okay, it's 4 o'clock, so let's go ahead and get started today. All right, good afternoon, everybody. How's everybody doing today?
Very good, thank you. And how are you doing?
Good, good. Yeah, anyone get rich off GameStop stocks?
Not if they were on Robinhood.
Man, I had to call my my friend who's an accountant to explain stocks to me yesterday because I had no idea what was going on. But now I think I have at least a rudimentary understanding of it. But it's crazy the whole situation. Okay, and so today the plan is to do a little bit of review, and so we're going to be primarily going over lecture note 01. So that lecture notes is titled Math and Programming Review, but so I wrote these lecture notes last year, but I've decided to take this class in a different direction. So we're not going to be doing any of the programming. We're just going to be reviewing kind of the linear algebra stuff. Okay, and so since I think that's probably not going to take us the whole time, then I'm going to start the next lecture notes on the direct stiffness method. Okay, but at the very least for today, you know, I want to make sure that you guys are familiar with the matrix form of a set of linear equations, how to solve that in Matlab, and then one other thing which I like to call assembly. Okay. Okay. And so this is probably, you know, for a lot of you, maybe the first time you're seeing kind of the usual kind of lecture format. And so, you know, I usually don't like to do PowerPoints because to me, it feels really static. And if I have to adjust something, it's really hard. And so what I usually do is I write on my iPad here and I join the Zoom call on both my laptop and the iPad because of Zoom's excellent cybersecurity. But this is nice because this allows me to have basically like a whiteboard. So that's kind of the idea with this. But I know more than anyone that my writing on the iPad is pretty terrible sometimes. And so, you know, if there's at any point, you know, during the lecture where things you're not sure what I wrote down, and then just let me know. And actually, the sooner the better. So if you want to just, you know, say something in your microphone or put in the chat, say, you know, what is that? You know, that's please let me know because I know my writing on this thing is not the best. I even bought like a nice stylus and it's still kind of terrible. Okay. Okay. So one more announcement before we begin today. So on Tuesday, we're going to be doing our first ANSYS activity. So we're going to be working with ANSYS on that day, just to kind of introduce you to the software. And we're going to do kind of a quick project just so you can see how we can go from start to finish. And so to prep for Tuesday, I want everyone to make sure that you can run ANSYS. So if you can run it on your computer, go ahead and download the student version. So there's instructions for that on the course website. And so, you know, if you have a Windows machine and you have a pretty decent computer, you can do that. Or if you have a Mac, or, you know, you don't want to download the ANSYS students because it's a pretty big, it's I think several gigabytes. You don't want to install it on your computer. You can use the virtual computing labs too. And again, there's a video which I posted on the course website where you can learn how to access that. So before Tuesday, make sure that you have ANSYS sorted out. You either have it installed in your computer, or you know how to access it through the virtual computing labs. Because once we start on Tuesday, I'm going to assume that everyone has it and you guys can follow along. Okay. All right. So before we begin today, are there any questions on anything I can answer?
Yeah, Professor?
Yep. Mm-hmm.
I downloaded ANSYS to my computer, but the interface is like super small, and I don't know how to fix that.
On your, okay. Let's, can you show me after the lecture, and then we'll, I can help you debug that. Yeah.
Sure.
Okay. Okay. Yeah. And if you're having any issues with the, you know, with the interface or anything like that, you know, just let me know, and I can help you debug that. Okay. Okay. So let's go ahead and get started today. And so the first part of this lecture today is just going to be just review of basically linear algebra review. Okay. Okay. And so if you're kind of following along with the lecture notes, we're only going to cover maybe the first 3 or 4 pages of this. Okay. And the reason for that is, I'm after kind of trying this class a couple times, I really want to make sure we focus on the ANSYS and not really and kind of get away from the programming, because I'm saving that more for the graduate level finite elements. Okay. But at the very least, just for the theory that we are going to know, we're going to need to learn we're going to need to remember some linear algebra. Okay. Okay. And so what you'll find out is that, through the application of finite elements, what we usually end up with is a very large set of algebraic equations. Okay. Okay. And so by a set of algebraic equations, what I mean by that is, basically, we're going to produce, a system where we have maybe 10 unknowns, and we're going to have 10 equations to solve for those 10 unknowns. Okay. And so that was just an example, but, through a lot of, big finite element codes, it's not uncommon to have something like 1 million equations and 1 million unknowns. Okay. And so the process of doing finite elements is first getting that linear system of equations, and then having the computer solve that for you. Okay. And the reason we do this is that computers are actually really good at performing linear algebra. So if we can take a complicated problem, this is just in general, so not just in finite elements, but if you can take a really complicated problem and put it in the form of like a linear algebra problem, then the computer would be able to help you out with that. Okay. And so the form that we usually like to put our equations in is in matrix form. Okay. And so matrix form, maybe this this notation is familiar to you, is something like AX is equal to B. Okay. Where A right here, this is a n by n matrix. And so by n by n, I mean it has n rows and n columns. Okay. And this is often called the coefficient matrix. Okay. And so this matrix consists of all the coefficients in front of the unknowns in your equations. Okay. This X right here is known as your solutions vector. And so this is what you ultimately want to solve for. Okay. And the size of this vector is usually n by 1, or it's always n by 1. Okay. And so it's a column vector. Right. And then this B right here is also a vector. Okay. And so this B, I think sometimes traditionally it's called the right-hand side vector because it's literally on the right-hand side. But for the purpose of this class, we're going to call this vector the forcing vector. Okay. And the reason we call it the forcing vector is, once we start doing finite element problems, you'll see things like, loads and constraints and basically any kind of external effects or any kind of external forces. Those effects tend to be put into the forcing vector. Okay. And just like the solution vector, it is a column vector. And so it has n rows and only one column. Okay. Right. And so what we're going to review today is how to take, a set of equations, a set of linear equations, and then put them in matrix form. Okay. And so just to kind of summarize the process, what we're going to be doing is taking our set of equations, extracting the coefficients. Okay. Okay. Take those coefficients, and then we're going to insert them into the appropriate spot in our coefficient matrix. Okay. Okay. And then we're going to do a couple examples just to kind of show this process, because it's, I think it's probably best illustrated with examples. Okay. And the nice thing is that, because this is not a linear algebra class, once we kind of set up this matrix form, we can then basically make Matlab solve it for us. Okay. So I know Matlab is kind of intimidating for a lot of people, but this part's really easy. So all we basically have to do is define the matrix, define the forcing vector, and then just tell Matlab to solve it. So it's at most going to be like 3 lines of code. Okay. All right. Any questions on this before we jump into an example? Okay. Okay. So let's look at this example. So let's look at a simple 3x3 system first. Okay. And so let's take this set of equations and then put it in matrix form. Okay. Okay. And so our first equation has been given by this. Okay. And so first equation will be 6x1 plus x3 is equal to 7. Okay. Our second equation will be 4x2 plus 7x3 is equal to 9. Make this 3 a little bit more clear. Okay. And then 3, we have x2 plus 2x3 plus 8x1 is equal to 11. Okay. Okay. And so here is our list of 3 equations. And you can see here we have 3 unknowns. So we have unknown, and I've labeled them x1, x2, and x3 just for simplicity. Okay. All right. And so the way we're going to put this into matrix form is that each of these equations is going to represent 1 row in the matrix. Okay. And so we're going to have basically 3 rows in our matrix and 3 different columns. Okay. Okay. And so, before we do that, let's go ahead and rewrite these equations just to kind of put them in a nice order. Because right now, our first 2 equations here only have 2 of the unknowns, and our third equation here, the unknowns are kind of ordered a bit differently. So sometimes it's kind of nice just to reorder them just so everything has the same order. Okay. Okay. And so, of course, this step here is optional. And so once you get used to solving these kinds of problems, you can kind of skip the step. But since this is our first example, let's go ahead and just rearrange the terms just to make it a bit easier on us. Okay. Okay. So let's start with the first equation. And so the first equation, you can see we start with 6x1. And so that's fine. So let's go ahead and stay that. Okay. All right. And so the next thing that you'll notice is that there's no x2 in this equation. And so even though there's no x2, just so that all 3 equations can have the same format, let's go ahead and put 0 x2 here. Okay. And And so this doesn't change the value of the equation. We just kind of added a 0 there, just to kind of emphasize the fact that x2 is missing from that equation. Okay. Then we have x3. Okay. And there's no coefficient in front of that. It's just 1. And then all of that is equal to 7. Okay. Okay. And so now let's do the same thing for equation 2. And so equation 2, you can see we're missing x1. And so let's do a 0 x1. Okay. Plus. You can see in equation 2, we have 4x2. So let's go ahead and bring that guy down. And then for x3, we have 7. So we'll have 7x3. Okay. And this is equal to 9. And then finally, for the last equation, you can see the unknowns are a little bit out of order. So let's start with the x1 term. And so we have 8x1, okay, plus x2 plus 2x3 is equal to 11. Okay. And so again, this step is optional here, but then from here it's really easy to go and pick these numbers off. Okay, and because what we're going to do is we're going to form a 3x3 coefficient matrix from this. Okay, and it's called the coefficient matrix because it literally is determined by these coefficients out in front of the terms right here. Okay. Okay. And so let's go ahead and write the first row. So the first row here is going to be 6, 0, and 1. Right? Those are just the coefficients that we read off those that first line there. Okay. Our next row right here is going to be 0, 4, and 7. Okay. That corresponds to the second equation. And then our last row is going to be our third equation here. So it's going to be 8, 1, and then 2. Okay. And so that's our coefficient matrix. So that's A. Okay. Next, we're going to write our solution vector. And so here we just need to have placeholders for the variables. We have x1, x2, x3. Okay. And then for the forcing vector, we're just going to take these values and then put them down here. So we have 7, 9, and then 11. Okay. All right. And so there's the matrix form of our system of linear equations. So usually at this point, probably you've learned it in your previous linear algebra classes. There's ways that you can solve this. I'm not sure what they teach nowadays, but I remember when I learned linear algebra, we learned things like an LU decomposition, right? And so you're welcome to do that. But since this isn't a linear algebra class, we're just going to have the computer solve this for us, okay? And so I know, if you have the features in your graphing calculator, then that works perfectly fine too. And so, whatever way that you want to use to solve this, then you can solve it. But just because I know a lot of you guys have MATLAB, I'm going to show you how to set this up in MATLAB and have MATLAB solve it for you. Okay. So are there any questions before we switch over to MATLAB? Okay. So let me go ahead and switch over to my computer. Okay. Okay, so here I have the MATLAB interface. I was testing out something earlier. Okay. And now we want to solve our linear system of equations here in MATLAB. So basically what we're going to do is we're going to set up, define each of the coefficient matrix and the forcing vector in MATLAB. Okay. So let's start with the coefficient matrix. Okay. So our coefficient matrix is a 3x3. And so we're going to define each of the rows in this matrix, okay? And so the way I like to do it is I just like to do, start with the first row, okay? So our first row is 6, 0, and 1. And so each entry in the first row, I'm going to separate with a comma. So I have 6, 0, 1. And then to go to the next line, I use a semicolon, okay? And so semicolon is a MATLAB's way of saying, go take me to the next row in this matrix. Okay. Okay, and so now we're going to enter the second row. And so the second row is going to be 0, 4, and 7. Okay. And so once again, I've separated each of them with commas. Right? And then I ended with the semicolon. And then for the last row, we have 8, comma 1, comma 2. And then since this is the last row, we're going to close with the square brackets and then a semicolon. Okay. Okay, so this is our coefficient matrix for our example. Okay. Okay. And so now that we have our coefficient matrix, let's go ahead and put in our forcing vector. And so our forcing vector consists of 7 for the first entry. Okay. Since it's a column vector, we're gonna separate these with semicolons just to tell it to go to the next line. Okay. 7, comma, or semicolon 9, semicolon 11. Okay. And so this is our forcing vector for our example. Okay. And then to form the solution, remember our system of equations look like this, right? So we have AX is equal to B. And so one way that you can solve this is you can invert the matrix A and then multiply it by B, okay? Okay. And so one way that you can say this is you can say X is equal to I and V. And so I and V is the MATLAB function for inverse, okay? And then we're going to call I and V on our matrix A. And then we can multiply that by B, okay? And let me leave the semicolon off here just so that we can see the solution, okay? And so once you've done that, you can go ahead and run the code. And here is your solution, okay? And so in order to satisfy these equations, x1 has to equal 1.0769. X2 has to equal 1.3077. And then x3 has to equal 0.5385, okay? Okay, so any questions on this? Okay, all right, pretty straightforward. But I'll show you kind of one other way that you can solve these equations. So inverse works, but it's kind of annoying because MATLAB doesn't like you to actually use the inverse function. And so another way that you can do this is you can use a special operator called backslash, okay? And so one way, another way you can do is you can do x is equal to a, and then you do backslash and then b, okay? Because solving, linear systems of equations is so common in MATLAB, MATLAB basically made a shortcut for it, okay? And so, just a little bit of MATLAB trivia for you too. This backslash is actually much more efficient than using inverse. Because this backslash actually tells MATLAB to use like an LU decomposition or some kind of smart way to solve this linear system instead of solving for the inverse. Okay, and so MATLAB typically doesn't like solving for inverses because it kind of takes a while, especially for a much bigger system. So this backslash, if you have a really big linear system, this backslash is actually going to be a lot faster. Okay, and so let's go ahead and run the code again. And you can see, we get the exact same solution. So you get x is equal to 1.07, exact same thing that we got for inverse. But this is actually the preferred way in MATLAB. Okay. But
so that what is it, / is essentially divide by the inverse, or?
Yes. So if you do
Okay.
/ this is just regular plain old divide. But this backslash is kind of like matrix solve. You can think about it.
Oh, it's multiplied by the inverse of A, right?
Exactly.
Or,
right.
Okay, got it.
Yes.
Awesome.
Mm-hmm. So either one will work. So, in this class, for the problems I'm going to give you, it doesn't really matter which one you choose. You probably won't even notice a difference. But if you do go on to use MATLAB, especially if you're in one of my other classes like 417 or something, we're going to use the backslash because it's going to be a lot more efficient for a system with like 500 equations, 500 unknowns. Okay. Okay. Any questions on this? Okay. So let me go back to my iPad. All right. And so linear systems of equations are going to be, pretty important for us, especially in the coming weeks, as we learn some of the theory. Okay. Okay. So let's do just kind of one more example, just really quickly, just to kind of hammer this home. Okay. And so let's do a system of 4 equations. Okay. And so let's do, I'm just going to choose numbers at random. So let's do 6x1 plus 7x2 plus 3x3 plus x4. And we'll say this is equal to 24. Okay. And now let's do 8x1 plus 4x2 plus 2x3 plus 7x4. And we'll say this is equal to 8. Okay. Next, let's do 11x1 plus 17x2 plus x3 plus, let's do 14x4. And this is equal to, let's say, 3. Okay. And then finally, let's do 3x1 plus 4x2 plus 5x3 plus 6x4, and this is equal to 7. Okay. And so here we have a system of 4 equations and 4 unknowns. Okay. Right. And so just like before, I'm going to pull off these coefficients here. Okay. And we're going to stick those into a matrix. And so because I just made this up on the fly, everything is in nice order, so we don't have to do any rearranging. Okay. And so let's go ahead and stick these numbers into the matrix. Okay. And so our coefficient matrix is going to be 6, 7, 3, 1, and then 8, 4, 2, 7. And then we have 11, 17, 1, 14, and then 3, 4, 5, 6. Okay. And so there's our coefficient matrix A. Okay. And then now we have our solution vectors. So this is x1, x2, x3, x4. Okay. And then finally, we have our forcing vector, which is going to be 24, 8, 3, 7. Okay. All right. And so again, to get the matrix form of these equations, it's basically just picking off the exponents. Okay. Rearrange them, and organize them if you need to. But then besides that, it's very straightforward. Okay. And then just like before, you can define these matrices in Matlab, and then simply just do either inverse of A times B or A backslash B. Okay. Okay. But if you have a graphing calculator, then go for that too. So do whatever you feel is best. Okay. Okay. Any final questions on matrix forms here? Okay. All right. So that's how we get a linear or a matrix form for a linear system of equations. Now we're going to do something that might be a little bit strange at first, but this is going to be something that's going to be central to our theory. Okay. And there's not really a name for this. And actually, if you look in finite element textbooks, they have a really, really stuffy and really confusing way of explaining this. But I think this is a little bit easier because it's more visual, but there's no name for it. So I like to call it assembly of smaller linear systems. Okay. 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 And so the reason we're going through this is that when we do finite elements and we perform it on a set of equation or a physical problem, what we're going to end up with is a bunch of tiny matrices. Okay. Okay. And the reason this happens is that, just like we talked about on Tuesday, when you perform finite elements, you have to discretize your domain. So you have to basically take your complicated geometry and then break it up into elements, right? So, you can think of it as we're essentially pixelating our domain, okay? And so when we apply finite elements to each of those elements, each of those individual elements will produce a tiny linear system, basically. Okay. And so the term that we'll use for these tiny matrices is called an element stiffness matrix. Okay. And so we use the term element is because, we'll have one of these per element. And then the word stiffness will be, I'll kind of save that for I think later on today. So that'll be more clear. Okay. And so the problem with this is that, we can't solve all these tiny little systems on their own. And so in order to actually properly solve the problem, we need to combine all these tiny matrices into one big linear system. Okay. Okay. And so the name I give for this kind of big linear system is I call it the global system. Okay. And so it's kind of one level up from all the elemental systems because it kind of incorporates everything. Okay. And so I think the best way to kind of illustrate this is with, again, an example. Okay. Okay. And so let's say that we have a global system with five unknowns. Okay. Okay. And so basically, as we start to do this finite element problem, we know that we're going to have 5 different unknowns that we're working with. Okay. And so typically the way that we're going to start is we're going to start with what's called an empty system. And so we're going to start with, since we have 5 unknowns, we know that we're going to have a 5 by 5 matrix. But for now, we're just going to assume everything is 0. Okay. Okay. And so it's going to look something like this. Okay. Right. And so let's say that, our solution vector has 5 unknowns. We have x1, x2, x3, x4, and x5. Okay. Next to this, we have a 5 by 5 matrix. But right now it's empty. So our coefficient matrix is empty. And so what that means is basically we have zeros everywhere. Okay. All right, and so what we're going to do is we're going to fill this matrix, with a bunch of little tiny matrices. Okay. Okay. And the way we're going to do that is, we're going to fit. We're almost. You can almost think of it as kind of like fitting like puzzle pieces into the right locations. Okay. And so to kind of help us with this, I'm going to label the columns in our coefficient matrix as well. Okay. Okay. And so you can almost think of this as kind of like coordinates on a coordinate axis, right? And so we have, each of the rows. So each of the rows are either labeled 1, 2, 3, 4, 5, depending on what row they're at. And the columns are also labeled 1, 2, 3, 4, 5. Okay. And so as we, put the smaller matrices in, you're going to see that we need to put them in the proper locations. Okay. Okay. Any questions on this before I turn the page? Okay. All right. So let's say that we need to insert the following element stiffness matrix. Okay. And so I'm just going to use coefficients or just kind of generic variables for now, just to kind of illustrate this. Okay. And so let's say that our element stiffness matrix looks like this. We have K sub A minus K sub A minus K sub A and K sub A. Okay. And this can be equal, multiplied by X1, X2. Okay. And then this is going to be equal to, we'll call it BA. Okay. And so let's label the columns here too. Okay. And so we want to take this kind of tiny linear system and then insert it into our global one. Okay. And so to do that, we need to take notes about, what variables are used here and here. Okay. Mostly on the right. Okay. And so we can see that this element stiffness matrix, it acts on the X1 and X2 variables. Okay. Okay. And so when we insert this into the global system, we're going to insert this into the X1 and X2 locations. Okay. Okay. All right. And so let's come back to the previous page where I had the global system, and let's find the locations where it's X1 and X2. Okay. And so you can see, X1 and X2, they consist of the first two rows of the matrix. Okay. And they also consist of the first two columns. Okay. And so where these guys intersect is basically on this and this little box right here. Okay. Right. And so you can see, just by design, the part that we've boxed here, which is, the first two columns of the matrix and the first two rows, it has the same shape as this elemental system that we want to put in here, which has, 2 rows and 2 columns. Okay. And so let's take all the values here in this matrix and then put them into that spot into the global system. Okay. So I'm going to go ahead and erase these zeros. Okay. And then let's do KA minus KA minus KA, KA. Okay. And so with that, we've inserted this first contribution to the global system. Okay. All right. And so we'll do a couple more examples where you can see, how things fit in. But before we do that, are there any questions on this? Okay. Okay. And so now let's do the following matrix. Okay. And so let's say that now we have KB minus KB minus KB, KB. Okay. Right. And now this matrix is acting on x2 and x3. Okay. Okay. And on the right-hand side here, we have BB and BB. Okay. Okay, so just like we did before, we're going to look at which variables that this is acting on. Okay. And we can see that this is acting on variables x2 and x3. Okay. Okay. And so what we're going to do is we're going to insert this into the x2 and x3 positions in the global system. Okay. All right, and so we're going to go to the x2 and x3 rows and also the x2 and x3 columns. And then just like before, let's put a box around those locations. Okay. Okay. And so what I've boxed in green right there, those are the x2 and x3 locations. Okay. And so just like before, we're going to put in the contributions. Okay. So we're going to change these zeros. Okay, so we'll do minus KB, and then KB. Okay. You'll notice that I've, that we have an overlap here. So we have an overlap on the x2 and x2 spot. Okay. And so we already have KA right there. And so whenever you have an overlap of two elements like this, you don't delete what was there before. What you're going to do is you're actually going to add to it. Okay. And so this entry right here now becomes KA plus KB. Okay. It's kind of hard to read. Let me go ahead and rewrite it. Right. And so we're going to have KA, and then to that, we're going to add KB. Okay. And so that intersect point is kind of the sum of those two contributions there. Okay. Right.
Dr. Chen?
Yep. Mm-hmm.
Just a quick question. Why are we not doing anything to the right-hand side, like the B in the global?
Good question, because I forgot.
Okay.
Yeah. So we need to do the right-hand side too. Okay. And so you can see in this first one, we have BA and BA. And so we're going to put those just like this. Okay. All right. And then for the second matrix, we have this guy right here. Okay. And so again, we have an intersect point. So whenever we have intersections, we're just going to add two things together. Okay. And so we're going to have a plus BB on the x2 row. And then for the third one, we're just going to have BB right there. Okay. Okay. Any questions on this so far?
Nope.
Okay. All right. So we'll do one more example. And where, so far we've done cases where, we have consecutive entries. So x1, x2, x2, x3. But you can also have cases where they're not next to each other. Okay. And so let's do this one. So let's do KC minus KC minus KC, KC. Okay. And let's say that this is acting on x3 and x5. Okay. Right. And so the same thing is going to apply. It's just that we can't group them all into one, one kind of big 2x2 block. Okay. And so this is going to be kind of scattered, scattered in the global system. Okay. Okay. And so, when I go back to the global system here, we're going to highlight basically each of those 4 entries. Okay. And so first we're going to go to the x3 row and the x3 column. And so that's going to be this guy right here. Okay. Then we're going to go to the x3 row and x5 column. So that's going to be this person right here. And then we're going to go to the X5 row and the X3 column. And so that's going to be this. Okay. And then finally, we have X5, X5, which is going to be this guy right here. Okay. Okay. And so just like before, we're going to add in our KCs here. Okay. And so in X3, X3, we're going to add KC since we have something there already. Okay. On the off diagonal terms, we have minus KC. And then on X5, X5, we have KC. Okay. And then on the right-hand side, we're going to add BC onto the third row, and then a BC onto the fifth row. Okay. Okay. And so that's just kind of an introduction on how we assemble these matrices. So I think probably starting next Thursday, we'll be working on problems where you can actually kind of see this in action.
Did you just arbitrarily choose the bottom right for K4? Because I'm just I got a little lost. I disconnected from the Zoom call for a second.
Oh yeah. So I chose those ones for blue because
they're arbitrary.
Yes. Yeah. So for this,
so you chose X5. I was for
exactly.
a second I thought you were going in order from 1, 2, 3, 4. I didn't know that you skipped to 5. So.
Oh yeah. So this was just to kind of illustrate that you can have cases where they're not kind of right next to each other too.
Got it. Okay.
Mm-hmm. Yeah. So right now this might kind of seem like arbitrary, like almost just like a weird game that I'm forcing you guys to play. But once we start to do some finite element example problems, you'll see this kind of in action. So right now it's really arbitrary, I know, but we're going to put this in play once we start doing problems with the direct stiffness metric method. Okay. Okay. So any final questions on this math review before we move on to the stiffness method?
Could you go back to the global matrix for just a second?
Yep.
Thank you.
Yeah, definitely. Mm-hmm.
Thank you.
Mm-hmm. All right. Any other questions on this? Okay. So that's all I wanted to talk about for the math review. So again, I know that there's more stuff in the posted lectures notes 01, but you don't have to worry about that because most of that's either going to come up much later in the class, or we're just not going to use it because we're not really going to be doing any programming. Okay. Okay. And so now we're going to move on to the next topic, which is going to be our lecture notes for next Thursday. And this is going to be the direct stiffness method. Okay. Okay. And so the direct stiffness method, you can kind of think of it as one way to implement the finite element process. Okay. Because actually, what we know as finite elements is actually kind of an umbrella term for like lots of different methods. And so there's different ways to implement this. So the direct stiffness method is just kind of one way to do it. And so actually, a lot of finite element textbooks start with direct stiffness because it's kind of the simplest one to understand and the simplest one to get going. Okay. And so we're going to do the same thing here. So we're going to start with direct stiffness. Just because even though it's relatively simple, and I guess honestly this method's not used that often for practical problems, I think it's a really nice starting point because it kind of brings together the entire process and it kind of relates it to a lot of things that you've seen before in previous classes. And so from this direct stiffness method, you're probably not going to be using this directly on practical problems, but it's going to be a launching point for for discussing things like element stiffness matrices, assembly, boundary conditions, interpreting results. So, this kind of has the lowest barrier of entry. So that's why I'm kind of choosing it with this. Okay. And in particular, today we're going to be talking a lot, or at least for the rest of class today, about something that you've probably seen a lot of in your time as an engineer, which is springs. Okay. And in particular, we're going to be looking at Hooke's law for springs. Okay. Okay. And so, we're going to kind of piggyback off this idea of springs because it's kind of a nice concept that I think, everyone has kind of seen before, at least to some extent. And then from that, we're able to build kind of a finite element method off this. Okay. And so just to kind of, give you a preview of what we're going to do is first we're going to, write down what the stiffness matrix is for a spring. Okay. Okay. When we do that, then after we do that, we're going to look at systems with multiple springs, or basically multiple elements. And then from there, we can assemble a global system. Okay, so that'll be assembly. Okay. And then the last thing that we'll cover, which is an important part of finite elements, is how to apply boundary conditions. Okay. Okay. Okay, so first let's start with what we know about springs. Okay. Okay, so let me draw a diagram here. And so let's say on the left right here, we have a fixed wall. Okay. And then to this wall, we're going to attach a spring. Okay, so we have a dot. And instead we're going to attach a spring. And then on this spring, we're going to pull it with some force F. Okay. And so let's say that the spring has an original length L, and then it's going to displace by an additional amount D. Okay. Okay. Right. And because it's a spring, it has its own spring constant. Okay. All right. And in this situation right here, we can relate, or we can form a relationship between the applied force and the amount of displacement. Okay. And that relationship is given by Hooke's law. Right. And so Hooke's law basically says that the force F that we apply on the spring is equal to our spring constant K multiplied by D. Okay. And this is basically our relationship. Okay. Basically what it says is that, when we apply force on a spring, it's going to displace, and that displacement is going to be proportional. It's going to displace according to the spring constant. Okay. Okay. And so before we move on, I want to take a specific look at the spring constant K. Okay. And so, we know this as the spring constant, but, just for the purposes of our argument, I want you to kind of interpret it as something what's called a proportionality constant. Okay. Or almost like a conversion constant. Okay. Okay. Right. And the purpose of that constant is basically to convert in between force and displacement. Okay. Because depending on what the spring constant is, you're going to get different amounts of displacements for the same amount of force, right? And so let's say that you have two different springs. One has spring constant 1, which is maybe really high. Another one has spring constant 2, which is really low, right? And if you apply the same amount of force on both springs, spring 1 is not going to displace that much because its spring constant is really high. Whereas spring number 2, maybe you might be able to stretch. Maybe it's like a slinky or something. You can stretch it, throughout your entire house. Okay. And the difference between that is the spring constant. Okay. Right. Another thing I want you to keep in mind is that this spring constant, it's kind of a very simple way to describe the properties of the material. Okay. Okay. Or in other words, it's a material property. Or in other words, it's not something that's external. It's something that's, inherent to the spring itself. It depends on, what the spring was made of, how it was manufactured, things that, are inherent to that spring. Okay? And that spring and that spring alone. Okay. And so this interpretation here is going to be important as we, derive kind of the element stiffness matrix for the spring. Okay. All right. Any questions on this? Okay. And so that's that diagram that I drew previously is for, when you have one end of the spring fixed. Okay. And so let's draw the same spring, but now let's generalize it so that, we can say that both ends of the spring can displace. Okay. Okay. And so let me draw our spring again. Okay. And so we'll call this thing on the left-hand side, we'll call this location 1. And we'll call the node on the left location 2. Okay. And we'll say that location 1 will displace by an amount d1. And then location 2 will displace by an amount d2. Okay. Okay. And then in order to create these displacements, let's say that we have a force F1 on the left-hand side, and then a force F2 on the right-hand side. Okay. Right. So instead of basically making a relationship between one force and one displacement, now we have two forces and two displacements for the same spring. Okay. And so now what we have is called a coupled system. Okay. Or in other words, we have two unknowns. Okay. Okay. And in particular, we'll say the unknowns are the displacements. Okay. Okay. And so instead of having just kind of one algebraic Hooke's law, now we're going to have, kind of a more generalized Hooke's law, right? And so instead of having one force on the left-hand side, what we're going to do is we're going to have two forces. Okay. So we'll say this is F1 and F2. Okay. Instead of having one displacement, let's say that we have two now, and we'll call them D1 and D2. Okay. And in the middle right here, this is where we're going to have our stiffness constant, right? Because this is before this is where our spring constant was, but now instead of a spring constant, so since now we have basically a two variable system, this now becomes our stiffness matrix, okay? Spring stiffness matrix. Okay. Right, and so this right here, this F1, F2, this is basically our forcing vector that we saw before. Okay, and then this D1 and D2, these are ultimately the variables that we're going to be solving for, and so these are going to be our solution vector. Okay. Okay. And so you can see, this is already starting to take a form that kind of looks familiar to us. Okay. And so the general form for this is, to not to display these in terms of their elements, but as something that looks like this. And so let's say that we have a forcing vector. So we'll call that F with a arrow on top for vector. Okay. We'll call the stiffness matrix K and the solution vector D. Okay. And so this is our general form. Okay. Where this is our forcing vector. This is our stiffness matrix. And then D is our solution vector. Okay. Okay. And so before we actually go and derive the stiffness matrix for a spring, I do want to take a step back and say that this form that I have right here, there's a reason I kind of wrote it as this generalized form, because no matter if you're doing a spring problem, if you're doing heat transfer, or you're doing fluids, believe it or not, every single type of finite element problem comes down to this form. Okay. Okay. And so, we can because all finite element problems come to this form, we can kind of generalize some descriptions of each of the players involved. Okay. And so let's start with the forcing vector. Okay. Okay. And so in our spring example right here, this forcing vector is literally, some forces that we're exerting on these springs. So these are kind of forces that we're maybe pulling with our hands or something. Okay. But in general, when you talk about just finite elements in general, this F is going to include any kind of external effects. Okay. Okay. And so any kind of external forcing. So these could be, literally like forces that we're, putting in right now. Or they can be things like heat fluxes for thermal simulations or boundary conditions. Okay, all of that's going to go here. Right. Next, let's talk about the stiffness matrix. Okay, and so the stiffness matrix, it's always going to contain material and geometric parameters. Okay. Okay. Or in other words, properties to this material itself. Okay. And that's really important because that's, you can see, we've kind of separated kind of external effects. You can kind of think of external effects as things that we're doing to our physical system. And then this material constant and the stiffness matrix here, this is going to determine its response. Okay. And so this solution vector D, this is another term for this is going to be our response. Okay. Right. So in other words, D is going to describe how our physical system is going to respond to the external forcing. Okay. And a lot of times, that's what we're interested in finite elements or just engineering analysis in general, is that, if we have this physical system, like say we have, this stylus or something, right? And then I take the stylus and then I just like smash it onto my desk, right? And so by smashing it onto the desk, that smashing, that's the external effect that I'm applying onto the stylus, okay? And then how the stylus responds, whether it breaks or not, whether it bounces back and hits me in the head, that's going to be determined by things like the geometry of the stylus, the type of material the stylus is made out of, the shape of the stylus, right? And so all of those things would go into the stiffness matrix, okay? And then its actual response, whether it bends, it breaks, it's, how it responds to the forcing, that's going to be computed by our solution vector D in this case, okay? Right. And so I wanted to kind of take a step back to kind of, talk about these things in general, because even though we're doing this for just a spring, you know, this interpretation of like an a forcing vector, a stiffness matrix, and a solution vector, you know, this is you know, this is a universal to all finite elements, and they all kind of have the same interpretation. Okay. And so, you know, for this class, we'll focus mostly on kind of structures and, you know, solid mechanics. But, you know, this framework of finite elements can be used for almost any kind of physics. Okay. Okay. Any questions on this? Okay. And so now let's actually, you know, take this spring system. Let's come back to springs, and then let's find out, you know, or let's derive what actually goes into this element stiffness matrix right here. Okay. 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 And so let's write out our system again. So we have F1, F2. Okay. And so let me write in kind of just generic entries for the element stiffness right now, and then we'll actually fill this in, you know, later. So let's call the top left entry, we'll call this K11. Okay. We'll call this entry K12. We'll call this entry K21. And then the bottom right, we'll call it K22. Okay. And our solution vector is still D1, D2. Okay. Okay. And so what we want to determine is what are each of these K values right here. Okay. Okay. All right. And so to do that, let's draw our spring again. And then let's assume that our spring is in equilibrium. Okay. Okay. And so basically our spring isn't displacing at all. Okay. And so let's see. So let's say that we, you know, here we have our spring at rest. Okay. Okay. And so here the spring is just, you know, it's just chilling. No one's bothering it. And then now let's say that, you know, we take the spring, we're going to grab it on each end and we're going to pull. Okay. And so the spring is going to stretch, but it's not going to translate. Okay. Okay. And so when we pull on both ends, you know, it's going to stretch and it's going to look something like this. Right. And so in order to make sure that our spring is in equilibrium, we need to pull it in each direction with an equal and opposite force. Okay. And so we can say that the force on this side is going to be T going to the right. And then the force on the left side is going to be T going to the left. Okay. Okay. And then just like before, we have our spring constant. And then, you know, since we're stretching it, now location 1 is going to go to the right. And location 2 is going to displace to the left. So now we have D1 that goes to the left and D2 that goes to the right. Okay. Okay. And so now let's form a relationship between the applied force T and the nodal displacements. Okay. 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 And so with this, you know, let's, we're just going to use Hooke's law for this. Okay. And so it basically, you know, we're going to use our force displacement relationships. We're going to say T is equal to K times gamma right here, okay? Where this gamma is going to be the total deformation. Okay? Or the total amount that the spring is deforming, okay? Right? Okay. And so we can actually express gamma in terms of d1 and d2, right? So since we know that d2 is going to the right, and so we can, if we draw kind of a coordinate axis here, so we say that anything that's going to the right is in the positive x direction, and then anything going to the left is in the negative x direction. What we can say is that the total amount that the spring is stretching, or its total deformation, is just going to be the difference in between d1 and d2. Okay, so we can say gamma is equal to d2 minus d1. Okay. And so when we plug this in, we can say that T is going to be equal to K times D2 minus D1. Okay. I'll do that on the actual here. So T is equal to K D2 minus D1. Okay. Okay. Any questions on this so far? Okay. All right. So now what we're going to do is we're going to relate T to the forces in this system, right? Because remember, in our original 2x2 system, we had F1 and F2. Those represent the forces that we're pulling on the ends with. Okay. Okay. And so, since we're applying T on both, on both ends, F1 and F2 are both going to be equal to T. But we need to choose the sign for it pretty carefully. Okay. And so let's look at location 1 first. Okay. And so on location 1, we have T that's being applied to the left. Okay. And so the way that we can express that is we can say that F1 is equal to minus T. Okay. Actually, let me write this on the next page. Right. And so we can say that F1 is equal to minus T. Okay. Since we're pulling point 1 to the left. Okay. And the left in this case is in the negative x direction. Okay. Meanwhile, on the other side, we can say that F2 is going to be equal to positive T, right? And the reason we choose positive is because, we're pulling point 2 to the right. Okay. And so if we plug in for T, because we have our equation for T out here, we can basically say that F1 is equal to minus K times D2 minus D1, okay? And F2 is equal to positive K D2 minus D1, okay? And so if we simplify this a bit, we have F1 is equal to K D1 minus D2, and F2 is equal to K D2 minus D1, okay? If we distribute the K through this, we can say that F1 is equal to K D1 minus K D2, okay? And then F2 is equal to minus K D1 plus K D2, okay? Right. And then from here, this is starting to look like our 2x2 linear system, right? And so just like we did earlier in this lecture, let's go ahead and pick off these coefficients, and we can finally form our element stiffness matrix for the spring, okay? Okay. And so our element stiffness matrix for the spring is simply just going to be the spring constant K, right? But just either positive or negative depending on which location that we're on, okay? And so this, this matrix, which I have right here, this is our element stiffness matrix for the spring. Okay. 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 Any questions on this before we sign off for the week?
No, all seems pretty good.
Okay. All right. So so remember Tuesday. So we'll pick this up again on next Thursday because Tuesday we're going to do our first ANSYS activity. So make sure you have access to ANSYS, and then you can follow along on Tuesday. Okay. And so with that, you know, we're at the end of the lecture. So have a good weekend, everyone, and I'll see you on Tuesday.
Thank you, Professor.
Professor.
I'll see you.
Thanks, guys.
Thank you.
Hey, Professor.
Yep. Thanks, guys. Chris, you wanted me to look at your ANSYS
Yeah.
interface, right?
Yes.
Okay. Let me go stop recording.